Learn physics with Dave.
Hello guys, let's solve some questions on waves, lenses, absorption and reflection of light waves in particular. Now this is contained in paper 2 of the AQA GCSE paper. Lenses are used to form images of objects. Figure 6 shows how a concave lens forms an image of an object. So here you have a diagram with the direction and the rays and all that, and how convex lenses and how concave lenses tends to form images. Now, there is one submission I want to make here. For concave lenses, the properties of the image is just virtual or virtual image. All right. So in this case, when you're drawing the line for your image, and then what you have is an imaginary line, I mean dashed lines, like what you have. If what you have is a dashed line, dashed lines, they're used in representing images formed virtually. All right. Now it says this image is upright. Yes, it's upright. What other properties can we use to describe this image? Yes, it's upright, the same orientation as the object. We can say that it's virtual. It's not real. When we say an image is virtual, we're saying if you have a screen and then you put the screen at the location of the image, you wouldn't get anything on the screen because it's imaginary. The rays appears, the image appears to form at that spot, but it's the otherwise. And the second description we can give this, if you check the size now, you would see that the size of the object is quite different from the size of the image. The object is, bigger than the image. So you can say here that the image is diminished. Now, moving on, figure 7 shows an object near to a convex lens. A concave lens is something like this, and then a convex lens is something like this. So the first one we solved here is a concave lens, and then the second question is on convex lenses. It says complete the ray diagram to show how the image is formed. Use an arrow to represent the image. So we're asked to, detect where exactly is the image formed when the object is between the principal focus and the lens. All right. Now, two rays is usually produced from the object. Okay, that's one of the principles when it comes to drawing ray diagrams and detecting where exactly, the location and the orientation of the image. All right. Now, the first one is the ray passing through the center. All right. The first ray is the one passing through the poles of the mirror. So we have this. You just have an arrow here. That solves the problem. And the second one is parallel to the principal axis. So you'd have a somewhat straight line here. But when it touches, the mirror, once the rays get to the lens, it will be refracted along the principal focus. So you have a point here, and then you have a point here. So you need to connect the two. Now, in this case, all we have to do here is to trace this image backwards. Now, if you're tracing it backwards, it means you're working with a virtual image. And your lines will have to be dashed because those are not the original rays. All right. So let's start with this guy now. Okay. So that's that. How do we now say the properties of this? Number one, it's upright. Number two, it's enlarged. I'm talking about the image now. It's enlarged. Well, again, it's virtual. The position of an image formed by a convex lens varies with the distance between the object and the lens. Figure 8 shows the results of a student's investigation using a convex lens. Now the question says, describe how the distance of the image from the lens decreases as the distance between the object and the lens increases. So what we're working with here is a graph of the distance of image from lens in centimeters and then the distance between the object and the lens. Now from this graph now, what we can deduce here is that as the distance between the object and the lens increases, the distance of image from lens will decrease. Let's have two examples here at 3.0 here for the distance between object and lens. At 3.0 centimeters, the distance of image from lens is 3.0 centimeters. Increase the distance between the object and the lens to 4, the image distance will decrease to 2.4. You can see that. Increase it to 5, the image distance will reduce to around this is somewhat around 2.14 thereabout, something along those lines. All right, yeah, let's work with our description. So here we can say that increasing the distance in the lens decreases the image distance more rapidly at the same object distance. All right, yep, that's that for the description. And then the last question here says the student, is that the last question? We have one more. All right, the student measured the distance from the image to the lens 4 times. The distance between the object and the lens did not change. The 4 measurements from the image to the lens were 1.9, 1.7, 2.2, and then 1.4. Calculate the uncertainty in the measurements. Now, the issue here is that in physics experiments, we tend to repeat, not only in physics experiments, science experiments generally, we tend to repeat them, multiple times for a fair test, because there can be, random errors as systematic errors, just to make sure that those things are taken care of. Now, for uncertainty, what you do when you're asked to calculate the uncertainty for this kind of question, you just do the largest value minus the lowest value, and then you divide that by 2. That would give you the uncertainty. So here now we have uncertainty equals to range. Range is just the highest value minus the lowest value when it comes to range of values divided by 2. So the highest value here is 2.2, the lowest value here is 1.4. We divide that by 2, and this should give you 0.4. Yeah, this should give you 0.4 centimeters plus minus. All right, and then here 4.5 says figure 9 shows a spotlight containing a convex lens. A red filter is placed in front of the spotlight. The spotlight is directed at a blue object, which is what you have on the screen. Explain why the blue object appears black. Now, this is one of the issues with absorption and reflection. What we see is just the reflection of colors. If you have a black object, the black objects will tend to absorb all the colors of the visible light spectrum. That's why it appears black. If you have a white object, it means that object will reflect all the colors of the visible light spectrum. So those are the two extremes. Yeah, in this case, we have a spotlight with a red filter. So what the red filter does is that it just allows only the red part of the visible light spectrum to fall on the blue object. Now, if an object appears blue, it means that it will absorb every color, the wavelength, each wavelength, every color of the visible light spectrum. It will absorb all and reflect that color you're seeing. So if an object appears green, that means it will absorb every other color: red, orange, yellow, blue, indigo, violet. It will absorb all of those and reflect green. So here now, the red filter is making sure that the wavelength of light falling on the object is that part of the red spectrum. So in this case, the blue object will just absorb that. So there is no blue color. There's no wavelength with the blue spectrum falling on the object. So now let's put all of that in words. So here now, for the spotlight, we can see that only red is transmitted from the filter. That's our first submission. Now about the absorption, we can say that the red is absorbed
by the blue object. So no light is reflected by the blue object. All right, so guys, that's that for that. That would be all for this particular question. If there's any part that you do not understand, you can just replay the video and rewind and watch it again. So that'll be all, guys. Thank you very much, and I'll see you in the next video.